At the edge of a black hole, if you turn around, you wouldn't just see one version of yourself, you'd see dozens, even hundreds. Not magic. This is the photon sphere, where light bends so strongly it can loop around the black hole, showing you multiple paths of your own image. But wait about 15 seconds, and even light can no longer escape your eyes. You've crossed the point of no return. So what really happens if you fall into a black hole? This isn't science fiction. This is based on hardcore physics. Before we drop you in, let's rewind. What is a black hole? Even Einstein once doubted they could exist. He described them as a place where physics breaks down, almost like dividing by zero. But the universe had other plans. When a massive star reaches the end of its life, it collapses under its own gravity. Everything compresses into an incredibly small point called a singularity, a place of infinite density and unimaginable gravitational pull. According to general relativity, gravity isn't really a force. It's the bending of space-time itself. Planets like Earth don't orbit the sun because they're pulled. They're simply following curves in this warped fabric. And a black hole? That's where this curvature becomes so extreme that escape is no longer an option. Inside a black hole, there's no solid black surface. What's hidden within is a singularity, so incredibly dense that it warps space-time into something like a bottomless well with vertical walls. Back in 1939, Einstein himself published a paper arguing that stars collapsing into such a point wasn't realistic, that black holes wouldn't actually form in our universe. But here's the twist. That very same year, J. Robert Oppenheimer and physicist Hartland Snyder published a groundbreaking paper suggesting the opposite, that massive stars could indeed collapse under their own gravity and form black holes. So what happens if you fall into one? Here's the wild part. A black hole doesn't care what you are, star, planet, or human. If enough mass is compressed into a small enough space, it becomes a black hole. That size limit is defined by something called the Schwarzschild radius, discovered by Carl Schwarzschild, who found the first exact solution to Einstein's equations. Simple, elegant, and terrifying. For something like our sun, if all its mass were squeezed into a sphere just a few kilometers wide, it would instantly become a black hole. If you compressed all the sun's mass into a sphere just 3 kilometers in radius, boom, it becomes a black hole. What about Earth? It would have to shrink down to a sphere about 9 millimeters across, basically the size of a marble. And a human? That's where it gets brutal. You'd need to be compressed to something far smaller than a proton, an almost unimaginable scale. But technically, if you could reach that density, you'd become a black hole too. So which black hole should we throw you into? We could pick a small one, but that's kind of boring. Let's go bigger. Some black holes have event horizons larger than our entire solar system, with billions of times the sun's mass. That's a bit extreme though, so let's choose one closer to home. Meet Sagittarius A star, the supermassive black hole at the center of our galaxy. You're actually orbiting it right now, along with the entire Milky Way. It's also one of the very few black holes humanity has ever directly imaged. Now let's set the scene. You and I travel there and park our spaceship about 1 trillion meters away from its event horizon, just on the edge of the unknown. We're sending you toward the black hole. You'll be in free fall, while I stay back on the spaceship, watching everything unfold. Now here's the crucial part. According to general relativity, time near a black hole doesn't behave the way we're used to. It gets distorted. The closer you get, the more extreme it becomes. Movies like Interstellar actually showed this effect pretty well. So to track it, we give you a special watch. It displays 2 times, your time and mine, back on the ship. We sync them. You take a breath and begin your descent. Almost immediately, the black hole comes alive. In the distance, you see matter spiraling inward, forming a blazing accretion disk. Gas and dust collide, heating up to unimaginable temperatures. The light is so intense it glows blue-white in reality, but in our simulation, it appears orange, just to make things easier to see. You check your watch for the first time. Only 30 minutes have passed for you, and you've completed just 0.1% of the journey to the event horizon. Up here on the ship, I've only experienced 11 seconds more than you. For now, time still feels almost normal, but it won't stay that way for long. The time difference still isn't too extreme, but we're getting closer now. Around you, space-time is warping harder and harder, creating bizarre visual effects. Light from the sides, even from behind the black hole, gets bent before it reaches your eyes. You're not just seeing what's ahead anymore. You're seeing the universe wrap around you. You check your watch again. From your perspective, it's been 2 hours. You've only completed 1.4% of the journey. Up here on the ship, I'm now 44 seconds ahead of you. It's noticeable, a little unsettling, but still manageable. Meanwhile, something strange is happening. The dark shadow of the black hole is growing faster than expected. That's gravitational lensing. Light that should have missed you is being bent inward, focused straight onto your eyes. Time passes. You check your watch again, and this time it hits differently. For you, about 12 hours have passed since you started, but for me, I've been watching you fall for nearly 15 and a half hours. We're getting dangerously close now. Things are about to get very weird, because before you reach the singularity, you're about to enter one of the strangest regions in the universe. Now imagine this. If you could somehow freeze in time and look around, the view would completely shock you. You've reached the photon sphere, one of the strangest regions in the universe. Here, gravity is so perfectly balanced that light itself can orbit the black hole. Not reflections, not illusions, actual photons trapped in circular paths. If a beam of light moves at just the right angle, it loops endlessly, but even the slightest shift, and it either falls in or escapes forever. It's a razor's edge. Now here's where things get truly surreal. As you look around, you start seeing yourself behind you, beside you, everywhere. Light from your own body is bending around the black hole and returning to your eyes. You're seeing the back of your own head, your shoulders, multiple versions of you, all frozen in space, all staring into the void. No mirrors, no technology, just space-time, twisted beyond comprehension. For a moment, it feels like you're surrounded by silent copies of yourself, like you're not alone anymore. But you don't stop. You keep falling. You pass beyond the photon sphere, and now the black hole fills your entire vision. The universe compresses into a thin ring of light around you. It no longer feels like you're approaching it. It feels like the darkness is swallowing you whole. This is because the darkness around you is no longer just darkness. Space-time itself is bending, revealing the back and sides of the black hole's shadow, along with regions that, in normal space, would never be visible to you. You've now been falling for 13 hours. In just 24 more minutes, you'll reach the event horizon. But from my perspective on the ship, I've already been watching your journey for nearly 20 hours. Time keeps stretching. Another 18 minutes pass for you. You check your watch again. For me, it's been almost 40 hours. Your final 18 minutes have lasted 18 full hours on my clock. And now, the final moment approaches. In just 6 minutes, you will cross the event horizon. You close your eyes, take a deep breath. You look at your watch, and something feels wrong. It says I've been watching you fall for an infinite amount of time, but it's not broken. That's just physics. From where I stand, I could spend decades watching you fall slower and slower, never quite reaching the edge. Your light stretches, turning red, fading into infrared. Eventually, I can barely see you at all. And here's the truth. I will never see you cross the event horizon, even if I lived forever. For you, those last 6 minutes, for me, they last an eternity. It sounds like science fiction, like a dream, but this is real. It comes straight out of Einstein's equations. Now, you've crossed the event horizon. Strangely, you barely notice the moment it happens. There's no sudden wall, no impact. You can still look outward, see distant stars, even spot our spaceship drifting far away. But everything you see, every ray of light, is now falling inward, just like you. You've passed the point of no return. Ahead lies the singularity, a point of infinite density where the laws of physics completely break down. Time, as we understand it, loses all meaning. To escape its pull, you'd have to move faster than light, and that's impossible. There's a common myth that from here, you'd witness the entire future of the universe unfold before your eyes. But that's not what really happens. As you fall deeper, something called aberration takes over. The outside universe doesn't expand, it compresses. All the light from the cosmos gets squeezed into a thin, bright ring above you. Everything else fades into darkness. And then, as you get closer to the singularity, gravity begins to stretch you. Your feet are pulled forward. Your head lags behind. The force grows stronger and stronger until space itself starts tearing you apart. Your body stretches, spaghettified, pulled into an endless thread. Piece by piece, you dissolve, becoming one with the black hole, drifting with it through the universe forever. It's terrifying to imagine, yet impossible to resist. Black holes, mysterious, beautiful, and utterly terrifying.